Hello. Hello. We'll begin in 5 minutes. So we'll begin in 5 minutes. All right.
Okay, okay.
All right. We'll start now. So hello everyone. I am Shubham Keshri. I am one of the TA for this course, Strategy and Introduction to Game Theory. I'm currently pursuing my PhD at the Department of Management Sciences, IIT Kanpur. And today is week 6 of problem solving session for this course. How this course will proceed, how this problem solving session will proceed is we will solve problems, and through those problems we'll try to understand the concepts behind those problems. If you have any doubt, you can just unmute yourself because you'll not be able to access the chat button in this meeting. So please don't hesitate to unmute and speak. All right. So we'll start. So this is the first problem. So first few problems are about the definition itself, and then we'll move on to more involved questions. So this is the first question, which is about first price auction, and it's asked you which one of the four statement describes first price auction. So you can take a minute and then respond the answer. And why are these important before beginning? Because in this week we had discussed auctions, and whatever we'll do past this will require the idea of what first price and second price auction is. Okay, so this is the first question where please go through the four options and tell me which statement corresponds to first price auction.
Option D,
Option D.
last option.
Okay. So you see this first price auction, you're saying that it is the highest bidder wins and pays the price equals to the his his bid. So you see in an auction there is two important things to take care of. What is the winning? How do a person wins and what he pays? So winner is decided on highest bid in first price auction. There are some Chinese auction as well where winner is not decided on the highest bid. He is decided in a probabilistic manner. I'll show you one. I'll show you. And what he pays the highest bid or his own bid. So what I was talking, so in this case, this first prize auction says the highest bidder wins and he pays the highest price. So what I was talking about is a Chinese auction where suppose there are n players, and player I bids Bi. So his probability of winning, so player I wins. So I wins. So this probability is actually given by Bi by summation of Pj j not equal j over all I, over all j it means. So this is one example where winner is not decided on the highest bid, where he is decided on the probability. So this is the probability of winning the bid. Okay. So this is another kind of auction. So there are multiple kinds of auction. So this is the first prize auction. All right. Any questions? Okay. So this is about second prize auction. So please go through the options and let me know what do you think is the correct answer of this question. How is winner decided and what he pays?
A option.
Sorry,
First one.
first one. So he pays. So second highest bidder wins, and he pays price equals to the highest bid.
Sorry,
Is
sorry,
the
Ulta. The first highest bid wins and pays the
highest
second highest.
right? So this is correct. So who wins? Highest bidder wins, and he pays a price equals to the second highest bid. So I have a question for you, a follow-up question. Suppose there are two situations: auction one A1 and auction two A2, and there are four bidders. In first auction, these are the different bids, and in second auction, these are the different bids. So first tell me, so this is player 1, player 2, player 3, and player 4. Similarly, player 1, player 2, player 3, player 4. So in A1, which is the who is the winner? Who is the winner?
P1.
E1. What he pays?
90.
90. All right. In second case, who is the winner?
Between P1 and P2, I don't know.
Okay, P1 or P2. So there should be some criteria on ties. All right. There should be some criteria on ties. Suppose in A2 the tie breaking rule is the player with the least index wins. During tie, player with least index wins. Now tell me who is the winner.
So P1 is the winner and he will pay 100 because that is the highest amongst the remaining bids.
Correct. So P1 will win and pay 100 and not 80. All right. So it is not the highest among the losing bids. It is second highest bidder, which is 100 and not 80. All right. So these two things you have to be sure what make a note of what happens. Okay. So before we begin solving problems of this week's lecture, I wanted to discuss some concepts regarding probability because I saw that there are some confusions regarding this. All right. So I'll move to the notes and then I'll discuss some concepts on probability. Okay. So So this is a kind of detour. It will not take less than 15-20 minutes. All right. I'll try to wrap it up, but it is important to understand these concepts. Okay. First, what is probability? You can respond if you want. All right. Instead of me just telling you what the concepts are, we can just come discuss. What is probability?
Chance of an event happening.
Chance of an event happening. So you see, probability is not actually chance of event happening. It is not chance of an event happening. It is not that. What is probability? Probability is actually a measure of uncertainty. So what does probability do? Probability tries to measure uncertainty. So it can measure the chance of an, so it measures the chance of an event happening, and not, it is not just a chance of event happening. It is a measure of uncertainty. What is the uncertainty in this case? The chance of an event, a random event to occur. All right. So I'll say probability is a function. If you don't know what a function is, you don't have to understand. Just think of it as a black box. All right. It takes some input and it gives output. The input of probability function is actually events. It takes inputs as events. And what does it give an output? It gives a real number. It gives a real number which is in between 0, 1. Right? Both included, 0 included and 1 included. For example, if I say I have a fair coin and I roll toss that coin, the probability of head occurrence for a fair coin is half. So you see, this function takes a input, which is the event. What is the event of head to occur? And the output of this function is a number which is between 0 and 1. So you see, this is half, which is between 0 and 1. So it cannot be less than 0 or greater than half. If both included 0 and half, the output will be such that it is included, it is in between 0 and half, both included. Right? So this is what probability is. Probability is a measure of uncertainty. Right? Now, this probability function has some characteristics. All right. If you have a random function which takes inputs as events and gives an output which is in between 0 and 1, will not qualify for will not qualify as a function of probability if it doesn't satisfy those characteristics. All right. So those are known as axioms. Axioms of probability. And why I am discussing this, you will see in subsequent questions. All right. Axioms of probability. So the first axiom of probability is, suppose A is an event and I'll say probability of A is greater than equals to 0. All right. So this is from the definition of the function, but these characteristics you will see, actually, if you define all those characteristics, you don't need to define the range of output. So I'll tell you what it is. The first axiom is probability of any event is greater than equals to 0. The second axiom of probability is probability of the sample space is equals to 1. And the third axiom of probability says, if A and B are two disjoint events. What do you mean by disjoint? I'll just tell you in a minute. Then probability of A union B is given by probability of A plus probability of B. Disjoint event means that there is no outcome common in between A and B. So what do I mean by that? Suppose, so this is a Venn diagram. Suppose this is event A, which has multiple outcomes. So an event can have multiple outcomes. For example, but an event which says that even number occurrence of a die. So even number can be 2, 4, and 6. So all those are outcomes of those events, and A constitute 2, 4, and 6. So A is one event and B is another event. And you see, there is no outcome in common. When there is no outcome in common in between two events, then we say A and B are disjoint. All right. Therefore, when this happens, when two outcomes are disjoint, then the probability of A union B is given by probability of A plus probability of B. Now, what I was saying is, when you specify these three axioms of probability, you don't need to specify this range of the probability function. This will be automatically satisfied when the three axioms are satisfied. Therefore, probability function is just a function with output, or you can say the range as R. the real number, the real line. All right. So these three are the axioms. And why is this? I am telling you this because you see, there was a question in discussion forum which was about something related to this, and we'll see what happens. Okay. So this is the first thing I wanted to discuss in probability axioms. The second is the second thing which I wanted to discuss is expectation. So expectation can be obtained for a random variable. All right. So what is a random variable? Random variable are variables which can take values which are uncertain. Okay. What do I mean by that? I mean by that is random variables can take multiple values with certain probability. All right. So for example, if I say random variable r takes value 0, 1 and 2. So it can take value 0, suppose by probability 1/3, half by probability 1/3, and 2 by probability 1/3. So the probability mass function, which is given by probability, so this is capital P, probability r equals to 0 is equals to 1/3, r equals to 1, which is 1/3, and probability r equals to 2, which is 1/3. So this is actually known as probability mass function. It says that probability capital R takes a value of R. So capital R denotes a random variable and small r is the particular value it is taking. All right. So this is equals to 1/3, 1/3, and 1/3 for r is equals to 0, for r is equals to 1, for r is equals to 2, and 0 for r otherwise. For any other r, it is 0. So this is known as probability mass function. Right. So how do we calculate expectation? So you see, expectation of, so I have taken r as the random variable. Expectation is generally obtained for a random variable. So when I say expectation of r, so it is written like this: expected E of r. Expectation of r is actually summation of r times p of capital R. So it just means, so this sum is over the sample space. I'm not writing those technical details. It says that you multiply r and take the probability mass function. So you put this over here for each. For example, in this case, if you want to obtain the expectation of r, it will be, so the value of r can be 0. So it is 0 times 1/3. So this is 1/3, you see, for r is equals to 0, plus 1 times 1/3 because 1 is taking value. So r is taking value 1 with a probability of 1/3, plus 2 times. So this is the expectation of r. Right? Right? So this is what it means. You take the probability mass function, multiply that value random variable is taking, and then take the summation. So why are we discussing this? So you see, if you, we will discuss this again in the questions, but for the time being, to make you understand properly, in the discussion which professor had, you see, they were talking about expected revenue. The expected revenue was the revenue, the utility he is getting, or maybe expected utility we'll talk about. Expected utility. So it was utility, what he was getting as the utility into probability of winning. So this is, I'm talking about auctions. All right. So the utility he is getting when he wins into the probability of win, plus the utility he is getting when he loses into the probability of lose or loss or lose maybe. So you see, this probability of win and probability of loss are actually probability mass function. It says that P of X, I'm saying this random variable is X, is taking some value, which is this value, if X is equals to win, and this value if X is equals to lose. So you see, this is win. So this is the mass or probability when it is winning, and this is the probability when it is losing. And over here we'll put X. So what is x? X over here denotes this x over here. The value of x denotes the utility he is getting in winning times probability of win plus the utility he is getting when he loses times the probability of loss. All right. So this is how expectation of any random variable are calculated. It is actually the value the random variable is taking times the probability the random variable takes that value, and you sum it over all the possible values the random variable can take. So in this example, the random variable can take either 0, 1 or 2. You just take each value of r, so it can be 0, 1 or 2. So you say 0, 1 and 2 and multiply by the probability r takes that value. So it is 1/3, 1/3 and 1. And you see when I am saying 0 otherwise, so therefore it can take any other value with probability 0. So all those terms become 0. Therefore only these three terms come over here. And this is what the expectation of r in this example is. In a similar way, in the lectures, professor has calculated expected value of the utility he is getting. So the utility he is getting when he is winning times the probability of win plus the utility he is getting when he is losing times the probability of loss. So this is how utility is calculated. Similarly, in a similar way, professor has shown you the expected revenue, and we'll go there and we'll see how we are getting this using this expression, right, or formula you can say. So this is the second part which I wanted to talk about. First is the axioms of probability. Second is the expectation. Third thing which I wanted to talk about is independence of event. Okay? Independence. If you have any question, you can just ask me. Okay. Independence of events. You can have independence of random variables also, but it is not important for this course. Independence of events. This is the third thing I wanted to talk about. So you see, in the axiom of probability, we talked about two events A and B. When both the events are disjoint, probability of A union B. What is union? If you go back to sets, then you will see that you take all the outcomes of those sets together, then it is known as union. So probability of A union B is equals to probability of A plus probability of B, provided A and B are two disjoint events. Independence is something different. What independence helps us is that, so suppose A and B are independent. So if A and B are independent events, then probability of A intersection B. So this is whichever is the outcome which is common between event A and event B. What is the probability of that? This will equal to probability of A times probability of B. And this is also required for the questions given in this week's assignment. So that is why I have taken this concept over here. All right. So probability of two events, when you want to, sorry, probability of the intersection of two events will be probability of A times probability of B, provided A and B are independent events. All right. So if you go back and see the lecture assignments of this week, you will see specifically the term independent. So it will be like the valuation of the players are independent and uniformly distributed between 0 and 1, something like that. So this term is very important. This helps you get the probability of these kind of events, intersection of two events. For example, so when I say I have two coins and I am tossing the coin such that both are independent of each other. So first toss is not dependent upon the outcome of the first toss, is not dependent upon the outcome of the second toss. So probability of head intersection head, it means what is the probability the first coin is giving head and the second coin giving head, provided the both the coins are fair, is given by probability of head times probability of head. So over here I'm saying the first toss is independent of the second toss, and this will be half because I'm saying the coins are not biased, and this is also half, which is given by 1/4. So you can do this because both of the coins, both the tosses are independent of each other. So this is where independence comes. Okay. So these are the few concepts. Any doubt over here?
So this H union H hota hai ki, is it H intersection H when you call it the independent event half into half?
It is intersection. So you see when we toss two coins, the sample space becomes HH, TH, HT and TT. So when I'm not writing anything between two outcomes, so H and H, it generally means H intersection H. It means H in the first coin and H in the second coin. Right? So this is actually H intersection H. Similarly, this is T intersection H. Right? So first coin had a head and second coin has a head. That is why H intersection H.
Okay.
Okay. All right. So this is about independence. And this is about expectation, and expectation is important. Expectation is actually mean value. So both are very similar. I will say same concepts and discussed in different areas of mathematics. And this is about probability and their axioms. All right. So we'll move on to the problems now. So I had discussed about the axioms of probability, how we calculate expectation and independence of events, and not I have not talked about independence of random variable. I have talked about independence of events. All right. So these three concepts we have covered. So this is the first question. This is a first price seal bid auction, and it says that there are two players. So there are two players, and the valuation of each of the player is B1 and B2. Right? And it is uniformly distributed between 0 and 1. Which one of these is a Nash equilibrium? This is the question. Okay? If you have seen the lectures, then you will be easily able to identify. Otherwise, we'll solve this and then we'll see which one is the Nash equilibrium for this problem.
I've seen the lecture. Wait, yeah, we can go ahead.
Okay. So what is the answer you would say for this problem?
I think there are others also on the call, so let them also.
So which one of these you know is a Nash
D,
equilibrium for
the last one.
D? Okay. So we know that D is a Nash equilibrium. All right. So the solution of this is actually given in the lectures. I will solve a same problem in a different way in the next question. All right. So this is the next question. It is same as the previous question. In a little bit different tone it is written. So it is saying that we are playing a Bayesian first price seal bid auction with two players, player 1 and player 2, and their private valuations are independent and uniformly distributed between 0 and 1. And if the Nash equilibrium of the bids are of the form K times Vi, then what is the value of K? This is the question. So could you answer what is K?
That should be B.
It should be B. Okay. Now we'll see how to solve this problem. All right. So what we have over here is, it is saying that the bids are of the form Bi are of the form K times Vi. Okay, so can you tell me why we are stating that it is a Bayesian first price sealed bid option? Why is this term there, Bayesian? Any idea?
That's because the valuation is uncertain of the auction value. The valuation which is being bid is not the bid. The valuation of the players is uncertain. It is not known to
Right.
each other.
So you see, when suppose I am player 1, I know my valuation V1, but I don't know about anything about V2. Not anything, I don't know the value of V2. V2 can take any value between 0, 1 with uniform distribution. All right. So player 2 can be of any type. Player 2 can be V2 is equals to 0.01, V2 is equals to 0.5 or 2, something like that. It can take any type. Player 2 can take any type. So this is how Bayesian games were described. I don't know what type of player 2 is. So I don't know the valuation of other player. So this is a continuous extension of what we had discussed in last week. In last week, the type of the other player was discrete. It can be either of type 1 or type 2, something like that. Over here, we are saying that the type of the player, the other player is actually in a continuous interval 0, 1. We don't know the valuation, or we don't know what type he is, and this type can be anywhere between 0 and 1. All we know is this valuation probability or probability distribution function. It is distributed uniformly between 0 and 1. That is all we know. All right, so this is why this Bayesian term is there. Okay, so I'll just erase this one.
So one
And
question
we'll,
over here, I mean, maybe a silly doubt. This is also called incomplete information or no?
yes, this is incomplete information when I don't know something about the other player.
So
So
is all are all incomplete information games called Bayesian games or no?
you see, when you have some kind of distribution of probability, then it goes to Bayesian games. There can be other information asymmetry also. So you see, when we talk about this incomplete information, there can be several types of incomplete information. When I don't know the strategies of the other player, that can be one kind of incomplete information. There can be other kind of incomplete information as well. For example, information asymmetry. All those will come in Bayesian games only, but equilibriums may vary. I'll show you one example where a Bayesian game can have a Bayesian Nash equilibrium. It can also have weakly dominated Nash equilibrium. I'll show you. So this equilibrium concepts may vary, but those games are known as Bayesian games because there is some kind of uncertainty in the game. So what I was talking is, I'll forget. So I'm talking about, you see, incomplete information can reflect many things. So over here, the incomplete information is I don't know what the type of other player is. I know the strategies. I know the strategies, but I don't know what is the type of the other player, and that determines the player's utility. There can be other kind of incomplete information as well. For example, I am manufacturer and you are a retailer, and my cost price of the product I'll not tell you. I'll not inform you about the cost price of my product. So I am manufacturing price of that product. The retailer may get the object at some selling price, but he doesn't know. He's uncertain about the cost price of the product from the manufacturer. So this kind of um, incomplete information is known as information asymmetry. I know something more than you know, something like that. So this is known as information asymmetry. All right. This is also an incomplete information
Yes,
game.
okay, understood. Yeah, thanks.
Okay, so this problem we are saying that we want to find Bayesian Nash equilibrium of the form. So where the bits are of the form Bi is equals to AVI. All right. So this is the form of uh, the strategy or equilibrium strategy of the players. So why are we specifying this kind of expression, or you can say uh, form of uh, the bits? Because there can be other Nash equilibriums also, and checking. So you can have two kind of questions. Verify. So in the last class we had talked about this. Verify that x comma y is the only Nash equilibrium or Bayesian Nash equilibrium BNE, and verify that x comma y is a Bayesian Nash equilibrium. These two kind of questions are very different questions. In the first question, you have to check that this strategy set is the only Nash equilibrium in the game. So you have to see that both the best responses are matching, and there is not matching, intersecting, and there is no other Nash equilibrium in the game. So there is no other intersection of best strategy. In the second case, you just have to check if the best response of the first player and the second player intersects at these points. Therefore, this is a Bayesian Nash equilibrium. Therefore, you can just say when player y, so when player 1 is playing x, the best response of player 2 is y, and when player 2 is playing y, the best response of player 1 is x. So when you just solve for this, you are solving for this. Therefore, this strategy x comma y is a Bayesian Nash equilibrium. You cannot say that this is the only Bayesian Nash equilibrium. Is this all right?
Yes.
Therefore, when we are specifying find a Bayesian Nash equilibrium of this form, therefore we are actually making the problem a little bit easier to solve. We are saying that find a Nash equilibrium of this form. There can be other Nash equilibriums also, and it will be a time consuming to solve for all Nash equilibriums. All right. Therefore, this expression is being given. Now we'll see how to solve this problem. Okay, so when we are saying that bi is of the form this, then we will say let. So we have two players. So I'll just say b2 is equals to kb2. Okay, we have only two players, player 1 and player 2. Let player 1 play b1, or let it be b1, or we can just say b also, no problem. Now you see, since this game is of incomplete information and I don't know what is the type of the other player, we will not be able to calculate our utility. We can only calculate our utility in expectation. So expected value of utility of player 1, expected value of utility of player 1 will be given as the utility he is getting when he is winning times the probability of win plus the utility he is getting when he loses times the probability of loss. So that is why we had discussed about expectation in my earlier part of this lecture. So you see, in this game, this is a first prize auction. When he wins, the utility he is getting is, you see, his valuation is V1. So V1 will be known to player 1. Player 1 will know his valuation. He will not know the valuation of the other player. So V1 is known to him. And in first prize auction, he pays exactly his own bid. So his bid is B1. So let V1 minus B1 times the probability of win. And if he loses, he gets a utility of 0. So this part just vanishes. So I'll just erase this part. It is of no use for us. Okay. Now, what is the probability of winning? You see, how will he win? He will win when B1 is greater than, or we can take equality, or we cannot take equality, just take equality. So when B1 is greater than B2. B1, when will B1 greater than B2? So B2, we have a value k times B2. You see, we do not know the probability density function or distribution function of B2, but we know the distribution function of B2. Therefore, we'll use this distribution function so that we can get the probability B1 is greater than KV2. Therefore, we'll use that. How to use that? We'll just say B1 by K is greater than equals to V2. And this kind of probability X is less than equals to X, is actually the distribution of X. If you know, have some knowledge of probability, this kind of probabilities are actually distribution of the random variable. So what does it say? This valuation V is less than equals to V2. And over here, so when I'm writing capitals, it means the random variable itself. When I'm writing small, it means that random variable is taking that value. So for example, over here, V is a random variable and it is taking a value of V2. All right. And we know this V2, which is V is less than equals to B1 by K. And in the lecture by professor, we had seen that this actually is given by, this will be given by B1 by K. This will actually become B1 by K. If you don't remember, you can ask me, I'll just reiterate how it is coming. All right. So when this kind of probability is coming for uniformly distributed random variable in the interval 0, 1, so whatever the value of V2 is, it will just take that value. So this is actually V2. So this is V2. What is V2? B1 by K. Right? So this will become V1 minus B1 times B1 by K. So this is the expected utility. So this is the utility in expectation. So some of the time I'll get this utility, some of the time I'll get that utility. In expected value, the mean value of utility is this value. Now what do I want to do? So this utility I want to maximize. So in calculus, you know, if you want to maximize a function, you have to take its derivative. Therefore, E u1 by d, what is the dependent variable? You see, we want to calculate b1, so we will differentiate in terms of b1 and not v1, because v1 is known. We want to know what is that value of b1 at which the expected utility becomes maximum. All right. So this is just b1 by k minus b1 square. So it will become b1 by k minus 2 b1. All right. And if you equate this to 0, then you will be able to get the value of b1, which is equals to b1 is equals to um, v1 by k 2 v1 by 2. All right. Have I done something wrong? If you see that I am doing something wrong, please let me know, right? Sometimes I make mistakes. Is this okay? Or have I done something wrong? Okay, so this is also K. And K over here, K will just vanish. All right, now it is all right. Is this all right?
Probably, yeah.
Okay, now you see when player 2 is playing KV2, when player 2 is playing KV2, player 1 is playing V1 by 2. So what is the value of K over here? Half times B1. Similarly, if you do for the other player, when you say B1 is equals to KV1, and you will get this half. Therefore, the value of K is half. Right? Now, keep in mind, this is for this kind of distribution where the random variable is distributed uniformly between 0 and 1. If you have some other kind of distribution, suppose it is distributed between 1 and 2 or maybe 2 and 5, in such case the value of K might change because the probability of win, that value, we have obtained that value using the distribution which is uniformly distributed between 0 and 1. If that changes, these values might change. So you have to be careful. That is one caution to keep in mind. All right. Any questions?
So assume that is 0 and 2. So we just have to the interval, the probability will still remain V1 minus B1 only.
So
What will
suppose
change?
there is a, I'll tell you. Suppose there is a random variable x, which is, so over here it is v. So let me write v. So what is v? V is the valuation of the other player. This is a random variable. Suppose it is uniformly, so it is written like this. It is uniformly distributed between a comma b. A and b can take any value. All right. When that is the case, then f, which is the distribution function of v, is given by, so when I'm writing capital V, it means the random variable itself. When I'm writing small v, it means the random variable is taking that value. This is given by v minus a by b minus a. So this is the uh, probability distribution function for a uniformly distributed random variable in the interval a comma b. Now, for our example, a is equals to 0.
Sorry, can you
Not our
explain
example.
this part again? I didn't.
Okay, I'll just explain once more. So what I'm saying is, what is V? V is the valuation of player 2 for in this problem which we are doing. It can be a player 1 also. All right, so player 1 and 2. So when I'm saying V is uniformly distributed, so when I'm writing like this, so it means V is a random variable which is uniformly distributed. U means uniformly distributed in the interval a comma b. So in our problem, a is equals to 0 and b is equals to 1 for our problem. You see, uniformly distributed between 0 and 1. For example, it was some other value a and b. If that is the case, the distribution function of v, so I'll write capital V, for any value of small v is given by v minus a by b minus a. This is the distribution function of capital V. So in our case, you see a is equals to 0, a equals to 0, and b equals to 1, so 1 minus 0, which is actually v. So in the lecture, you will see that when a professor had told you that, for example, you want to calculate what is the distribution of half. So you just take half and that length will be that distribution. So this is actually half. So you see V, capital V of V is actually small v. It is taking that same value. So over here you put half, you will get half. Over here you put v, you will get v. This only happens when a is equals to 0 and b equals to 1. If a and b are some other value, you will have to obtain like this. So for example, v was uniformly distributed between 5 comma 7. Suppose this was the case, then f b of v would be V minus 5 by 5 minus 7. In that case, this will be V minus 5 by 2 and not the length of the interval. And this probability you will have to put over here, probability of winning, and then you will have to calculate. And one more thing for clearly understanding, probability of V taking any value less than equals to V. So V is a random variable, capital V, and small v is the value random variable is taking. This is actually the distribution of V, right? So this value, which is what? This is actually probability capital V is taking any value less than equals to small v. Please ask me questions. These are concepts which might take time to understand. I will repeat everything again. I have no problem.
So can you just show what was the probability taken earlier? That was the interval, length of the interval, no? V minus, and now you are saying it will be V minus 5 by 2. It will not be the length of the interval.
No, because it was not uniformly distributed between 0 and 1. It can take any value, 5 and 7, it can take 0, 100 or any value in that case.
So here the probability, let's say this is the winning probability, it will be V minus 5 by 2 into the
utility, winning utility.
Into the expected winning utility.
Winning
okay.
utility.
Yeah, winning utility. And then plus the probability of losing into the losing utility.
Losing probability.
Okay. So
now
the probability of losing, just in case, let's say the losing utility was not 0, then the probability of losing utility would be 1 minus this entire V minus 5 upon 2.
Right. So why you could do that? That is also important. Why you could do that? You see, that is why I had discussed the axioms of probability. You see, when I said the second axiom was probability of the sample space is equals to 1. So you see, when winning and losing comes, the sample space consists of only two outcomes, win and lose. There are no other outcomes in the sample space, right? Win and lose. Either you can win or you can lose. So when I say probability of sample space is equals to 1, it means probability of W union L is equals to 1. All right, because W union L is S. Is this all right?
Yes, understood.
Now you see, from the third axiom, I said that probability of two outcomes, if they are disjoint, over here it is outcomes, but I had talked about events, then it can be written as probability of win plus probability of lose, which is equals to 1 from the third axiom. And we have probability of win. So this is the probability of win. You plug it over here, you can get the probability of loss. 1 minus probability of loss. How can you do that? You can do that using the axioms of probability. Probability of win is actually equals to 1 minus probability of loss. So these are the concepts behind all those. How are you able to get it by 1 minus those things?
Okay, clear. Thanks.
So yeah, this is it for this problem. Anything else?
No, thanks.
Okay. So these two problems were similar, all right? This problem and this problem. So this problem's answer is D, V1 by 2 and V2 by 2. Okay? As we have seen in this case, both are same problems. Little bit the formulation or the English is different, but the problem is same. Okay? So this is a second next question. So this is about expected revenue. So consider two players in a Bayesian first prize auction. Again, Bayesian I have written. Therefore, there is some kind of incomplete information involved. So we are talking about first price auction. So we can know that what is the incomplete information? The valuation will be the incomplete information discussed in the lecture, and the valuations are V1 and V2 for the two players, which are uniformly distributed in the interval 0, 1. What is the expected revenue of the auctioneer for the equilibrium bid? So there was some confusion in the expected revenue, and someone has mentioned that in the discussion forum, and that is why I had taken this problem over here. So if you know the answer, you can tell me. Otherwise, we'll see how the expected revenue is obtained.
Yeah, the expected revenue is 1/3 in all the cases.
1 by
3.
Right. So this is the correct answer. So we'll see how expected revenue is calculated, we'll use the concepts of probability we had just discussed, such that you will give a comprehensive idea of how expected revenue or any other expectation is calculated. So there was actually, what is the question in the discussion forum was, I'll show you when we do this. We'll show you where the confusion was. All right. So in the first price auction, what is the value, or what is the value the auctioneer will get? He will get so I'll write revenue. He will get B1 if B1 is greater than B2, and he will get B2 if B1 is less than B2. Is this all right?
Yeah.
So this combined can be written as maximum of B1 comma B2. Okay? This combined can be written as maximum of B1 comma B2. So this was the original function. We have changed this function in this way, and we are saying that this function and this function are equivalent. You have to see if this is equivalent or not. You see, when B1 is greater than B2, this function will take value B1, and when B2 is greater than B1, then this function will take value B2. Therefore, this function and this function are equivalent functions. Both are same function. Okay. Now this revenue, all right. Okay, so I assume it is all right. This revenue, so we know B1 and B2, the Nash equilibrium values of B1 and B2. What are that? It is half B1 and half B2. So it is actually maximum of half B1 comma half B2. So half is a number, we can just take it out, half maximum of B1 comma B2. Right? Now you see, this V1 and V2 are actually random variables. We don't know the value. All right. So you cannot obtain revenue, some value of revenue, since it is dependent upon some random variable. Therefore, you have to take expected revenue, because this variable is actually dependent upon a random variable. Therefore, revenue itself becomes a random variable. This revenue is a function of random variable. What is revenue? Revenue is a function of V1 and V2. And what is V1 and V2? V1 and V2 are random variables. All right. So therefore, revenue itself becomes a random variable, and it becomes uncertain. Therefore, what we'll do, we'll calculate the expected value of revenue. What is the revenue in expectation terms? All right. So if you remember our discussion, expected value of some random variable is calculated as summation of the value that random variable takes times the probability of that random variable, or the probability mass function of that random variable. All right. So um, this is the expected value. All right. Now you see this probability mass function. This r, this r can take two values actually. So I could say in other way. In other way, I can say that when v1 greater than equals to v2, when v2 is greater than or equals to, doesn't matter, v1. All right, because these are continuous values, it doesn't matter if you put equality or inequality, or just equality, sorry, inequality, or just less than equals to, or just less than. All right, doesn't matter. You can divide this probability into two parts. Right. So when v1 is greater than equals to v2, and when v2 is greater than v1. If you go back in the lecture, you will see that there are two scenarios. Professor has also, so it is scenario 1 and scenario 2. So the scenario 1 in the lecture was, I'll just write it over with the scenarios. It is saying v1 is the maximum. When v1 is the maximum, v1 lies in between. So I'll just write v1 belongs to b comma b plus d, and v2 belongs to 0 comma b. Therefore, v1 is maximum, and this is the case. All right. So we will obtain the probability of this case and probability of this case. All right. And you see, there are only two cases. Either this case can happen or this case can happen. So this is kind of a probability mass function. Either this case or this case. Only these two values. This only these two values could be obtained, or the probability could be calculated only these two values. So therefore, when I multiply this revenue which I am getting, for each of the cases, we'll obtain the expected value of revenue. Is this clear?
Yeah.
Okay. Now what I have to do is I have to calculate the probability of first case happening. Okay. So I'll just use whatever was done in the class. Okay. So it was done is probability v1 belongs to v1 comma v plus dv. And you see, when I'm saying this happens and this happens, so what does it mean? Okay, just, sorry. I mean this intersection v2 belongs to 0 comma v. Okay, this happens and this happens. Okay, this happened and this happened. Now I'll say these two are independent variables. Therefore, this is given by probability this belongs to v comma v plus dv times probability v2 belongs to v comma v. Okay, so you could understand why I'm multiplying. That was one issue in the discussion hour. Why are we multiplying? So this is why we are multiplying. This event and this event are independent. Okay, these are independent random variables. Is it not written over here? It is not written, but we have to assume that v1 is independent of v2 and v2 is independent of v1. Therefore, this event and this event are independent, and therefore we can multiply the. So what is the actual thing? Probability of A intersection B is given by probability of A times probability of B. When can we do this? When A and B are independent. Therefore, you see, this happens and this happens. When these two are independent, we can just multiply the probability. So this is how this is obtained. Is this all right? Am I going fast?
Clear.
So you see, probability of this happening. So it is actually dv. So if, because we are taking uniformly distributed between 0 and 1, we are just taking the interval length. Okay, it is dv, and this is just v. So it will become v dv. Scenario 2, so S2 is when v2 is the max. When v2 is the max, then v1 lies in the interval 0 comma v, and v2 lies in the interval v comma v plus dv. Same thing will happen just in the other way around. So we are saying find the probability of this, which is what? Which is v1 taking value 0 comma v intersection v2 taking value v comma v plus dv. All right. And since v1 and v2 are both independent of each other, we can just multiply their probability. So v1 taking value 0 comma v, sorry, times probability v2 taking value, sorry, v comma v plus dv. All right. And again, these are uniformly distributed between 0 comma 1. So this will become v times, and this will become dv. Okay. Now you see, this is v dv and this is v dv. The question in the discussion forum was, why are we adding these two things? So what it was there, it was saying probability of this happening is v dv plus v, v dv plus v dv. You don't need to do that also. You forget about that. You just use this expression and you will be able to obtain. You see, what is the revenue he's getting? The revenue is what? Revenue is this maximum of v1 comma v2, right? But in this case, you see the the case which we have taken is, so we will draw the line. It is uniformly distributed between 0 comma 1, and we said this is v and this is dv. So in both the cases, in this case or in this case, the revenue are for both the cases, for 1 and 2, for both the cases, revenue is actually V. Capital V, small v, doesn't matter. Over here, I'm writing small v. Is this clear? For this case, scenario 1 also it is small v. For scenario 2 is also small v. Because the maximum is v, comma v plus dv. And over here also the maximum is v, comma v plus dv. Therefore, the revenue for this case is v. Is this all right? Are you with me?
When you're saying the revenue, V1 is max and V2 is max. So why are you saying V is max?
No. Okay, I'll just repeat everything else. So this analysis which we are doing, this scenario 1 and scenario 2, is done for a strip of values. The strip of values is the maximum is V. The maximum value of B1 comma B2 is V. So what is the condition? The condition is V1 belongs to V comma V plus DV, and V2 is less than that, which is 0 comma V. So what is the maximum value? The revenue is V for the first case. For the first case, maximum of V1 comma V2. What is maximum of V1 comma V2? I'll write it. It is better to write it. Just write. So for case 1, for scenario 1, when V1 belongs to V comma V plus DV and V2 belongs to 0 comma V. This is the same scenario. The revenue is given by half times maximum of V1 comma V2. Okay. So you see V1 is maximum over here. So this will actually become half times V. All right. Similarly, in scenario 2 also, when we have V2 belongs to V comma V plus DV and V1 belongs to 0 comma V, we have revenue is equals to half times maximum of V1 comma V2. Over here, V2 is maximum, which will be half comma V. Is this all right? We're ignoring this part dV because dV is very small. So in both the cases, the revenue is coming out to be half V. Is this all right? This was actually half V. Is this all right?
This V is a variable V, not the valuation V1 or that's not your.
I'm sorry, I couldn't hear you. Could you just repeat?
I'm saying I was getting confused between V1, V2, and V. V is this variable V, is what you're saying.
Yes. So V is the value at which we are calculating all those things. If you go back to the lecture, we are saying that we will obtain the expected revenue for this strip V and V plus DV, and then we'll integrate it for the whole strip 0, 1. Currently, we are getting the expected revenue for this, not expected revenue, for the revenue for the strip V and V plus DV. For this strip, this is half V and this is half V. That all right?
Okay.
Now we know how to calculate expectation. We will say scenario 1. For scenario 1, it is half V times the probability. What is the probability of scenario 1? It is VDV plus half V for scenario 2. And what is the probability? It is VDV. So you see in the lecture, it was added VDV plus VDV. Over here also it is getting added. You see half V times 2 VDV. Half V times 2 VDV, and therefore that 2 dV was coming. 2 VDV was coming. This is coming from basic concepts of probability. We are getting expectation. How to obtain expectation? Take the value that random variable is taking, multiply with the probability, and submit over all the values it can take. So first value it can take is half V times the probability. Second value it can take is half V times the probability, and therefore we are multiplying. So these two scenarios can occur. Either V1 is more or V2 is more. No other scenario can occur. Either V1 is more or V2 is more. Therefore, we are taking this sum, and it will come out to be V square dV. The expected revenue for that strip V and V plus dV is V square dV. Is this all right?
Okay.
Now we'll integrate it. So we'll just integrate it. The expected revenue over the whole strip will be given by 0, 1, and it is V square dV. You integrate this, it will be V cube by 3, 0 and 1, which is 1/3. Therefore, the answer is 1/3. Is this all right? Or there is some doubt? I will just repeat everything if there is a doubt.
Just a minute. I'll just. Okay, fine. Yeah.
All right. So this is all the concepts which we had done about probability. You see, about independence, about the axioms, about expectation. So that is why we had taken that up before proceeding over here. Now, the second question is, when this is not uniformly distributed between 0, 1, there is some other, suppose there is some other kind of distribution. First, let us
Suppose it
consider,
is not 0 and it is something else.
right, suppose it is uniformly uniformly distributed between A and B. When that happens, then this value VDV might change. All right, it will be something else. But since it is uniformly distributed, the uh, uh, form will remain same. Now, if you change the distribution, if it is not uniformly distributed, suppose it is some other distribution, geometric distribution or normal distribution, some other distribution, then these probabilities have to be calculated appropriately. The steps which we have done will remain the same. This expected kind of which we are doing, integrating it, all those remain same. These probabilities, this probability and this probability, just that will change. So this value and this value will change. Nothing else will change. Everything else will remain the same.
Also that 0, 1, if it is instead of 0, 1, it is that pi and 7, which you showed in the previous page.
Right. So what it will do, this value is A, this value is B, you just write that value V minus A by B minus A. Right? So for example, when you are saying V1 belongs to V comma V plus dV, and what is this is A, this is B, F of V, oh, I'll just write it properly. So the distribution capital F, capital V of small v will be given by small v. So again, this is small v. I'll just write some other v bar. Okay, sorry. So it is v bar. So v bar minus v by v plus dv minus v. So it will become v bar minus v by dv.
Sorry, what is V bar? The mean.
Sorry?
What is V bar?
V bar is the value capital V is taking. So over here, you see, this is the distribution. Now you will have to obtain what is the probabilities taking value between V plus dV. So this is the distribution. So I have done slight mistake over here. All right. So what is the mistake? I'll tell you. Over here, what we are doing is we are trying to calculate the probability it is taking between V comma V plus dV. And this distribution is not that. Distribution, what it means? Distribution means probability capital V is taking any value less than small v. This is what it means. Okay. When you have to calculate this kind of probabilities, slight changes are there. So do you want me to go over there or will it become complex? I can go, I have no problem.
No, it's already complex. I didn't understand what is V bar minus V in the numerator of this. Why
No,
it is
so
V bar
over here,
suddenly?
okay, just give me a minute. All right. When I say x is a random variable, x is a random variable, and when I say f is the probability distribution of x, then it will be capital X of small x. This small x is the value capital X is taking. So that is why I have written v bar. You see, this a and b had v, so I cannot just say v because this v bar is changing. It can take any value 0, 1, 2, 3. But this v and v plus dv is fixed values, right? A and b. That is why I had made it v bar and not v, because then it will become 0, and that is not correct, by the way.
Okay.
Now, one thing I wanted to tell you, uh, please don't get confused. If you are getting confused, please stop me. All right. So you see, what is this probability? This is probability of probability. What is this probability? I'll just show you again. What is this probability? This probability is V. Um, this is V1. All right. So V1 belongs to V comma V plus dV. So what is this? V less than equals to V1 less than equals to V plus D. Is this all right? This and this are same. Are both the two things same?
Yeah. Yes.
Right? And what is this capital V? This is capital V and small v. What is this? This is probability V is less than equals to, over here it is V1, so I'll just add V1 is less than equals to small v. Is this all right? This is distribution. So distribution is given by this expression. Is this all right?
No, I'm not. Earlier,
Okay.
V was less than V1 on the left hand side for a term. Now,
No, I'm not talking about this. I'm not talking about this. This is altogether different. This is just the concept of distribution. Distribution is given like this. Distribution is given like this. That is probability. So if I say this, so this is what probability x is less than equals to x. This is what I'm talking about. It is not related to this currently. I'll just relate it. Is this all right? F capital X of S is actually P of X less than equals to X. This is the definition of the distribution function. You can talk to me instead of.
no, V1 was the valuation of the player 1. So in my mind, that is a fixed value, which is his valuation. So what you're saying is the probability that the valuation is less than the variable V.
So over here, actually, these are random variables V1 and V2. We have not written it in capital letters. What are we saying? You see, just read it. We are saying V1 and V2 are not known, and these are uniformly distributed between 0, 1. So actually, V1 is a random variable and V2 is a random variable.
So they are not fixed valuations of that there.
We have not written it capital V1 and capital V2 because that is how we are following in game theory. But in probability, when you are writing probability, when you are talking about probability, random variables are written in capital letters.
Okay, okay, fine.
So how? Okay, so okay, so I'll just go through the problem again. What have we done?
No, you can wrap it up. It's okay. Otherwise, we'll miss the next step also.
Sorry, I couldn't hear you properly.
I said you can complete this and then we can go to the next one. Otherwise, we'll keep on circling in this only.
Okay, so I'll just leave whatever I was telling you. Okay. So you see this problem, we had the distribution of random variables as uniformly distributed between 0, 1. You can have other kind of distribution. The steps will remain the same. You can obtain the expected revenue. All right. We'll move on to the next question. This is same as the previous question. You just read, slight differences there. Okay. Over here we have n bidders, n players, and the bid is of the form. Okay, so this is not a question of expected revenue. This is a question of best response. All right. So excuse me for that. Best response. So this is a question on best response. So we have n players, not 2 players, and I'm saying the bid of all the other players except player 1 is vi cube. What is the bid of? What is the best response of player 1? So there is player 1 and there is all other players. So I will belong to the set 2, 3, 4, n. So all these players are bidding bi is equals to vi cube. What is the best response of player 1? This you have to find. Is the question clear? And a similar question has been given in your assignment. Very, very similar. So I'm skeptic to solve this also. No problem, I'll just help you out. And you see, specifically it is mentioned this vi is independent. So all the random variables v1, v2, v3, v4, v5 till vn are independent of each other. So the independent concept which we had seen previously will come over here, and it is uniformly distributed between 0, 1. All right. So have you read the question clearly? Could you tell me how we'll solve it, provided you have read the question?
It will be half of V1 cube. No? That is the best response that you have seen. K is always half.
My microphone is not working properly. Could you repeat?
Is it going to be half of V1 cube because Vi cube because K is always half in first place field bit.
So I would suggest not to guess this, because uh, something which is happening might not be same over here, because the strategy is changing first of all, and second, we don't have only 2 players, we have n players. So we will see whether it happens to be half of v1 cube or not. It might happen, it might not happen. Before that, before getting me the answer, could you say what will be the steps to solve this problem? That is more important to understand.
I don't know.
You see what we had done earlier. What we do, we have, when we have 2 players, we will fix the uh, response over here, that the response is the bid or the strategy. So I'm saying all the other players are playing vi3. Okay, what will be my utility? So you see, this is a Bayesian game. This is a Bayesian game. So since this is a Bayesian game, I will not know my utility. My utility is dependent upon the type of the other player. We have n players, therefore will be dependent upon the n number of players. First thing. Second thing, this utility which I will get, I'll have to calculate the expected utility. All right, because this is a Bayesian game, we will not know our utility. Our utility will be dependent upon the random variables, that is the valuation of the other player. Therefore, we'll have to calculate. So the first step is to fix the strategy of other players, so which is already given, so we don't have to do this step of the other players. So how do we calculate best response? That is, I am telling you. So the first step is fix a strategy of the other player. For that strategy, get your utility. Over here, we will not be able to get the exact utility. We'll have to get the expected utility. Get the expected utility you are getting. So whichever the player is, so not you, expected utility of the player, of the considered player. So this is how we calculate best response. Third, maximize. So find that strategy. Find that strategy that maximizes this this utility. This is the steps of obtaining best response. Is this clear? That these are the steps of obtaining best response.
Okay.
Right. So we will follow these steps only. How we will do that might change, but the steps will remain same. First, fix the strategy of the other player, obtain your utility, and find that strategy which maximizes your utility. All right, this is all we will do. So you see, first step it already done. We are fixing the strategy of all the other players as V1 cube. By the way, a similar problem has been given in your assignment. So I might not solve this. I'll give you the steps to solve this. All right. So this is the strategy of the other player. What will be the expected
This is
utility?
Vi cube, right? Not V1 cube.
Sorry, this VI cube. Over here it is written VI cube. Okay. So what it is? So B1 will play B2 will play V2 cube, B3 will play V3 cube, and so on and so on. Okay. Each player will play its valuations cube.
Yes.
Now we will have to calculate the expected utility of player 1. The expected utility of player 1 will be the utility he is getting times the probability of win when he wins, the utility he is getting when he wins, times the probability of winning plus the utility he is getting when he loses times the probability of loss. So this is a first prize auction. In first prize auction, the utility he will get when he wins will be V1 minus V1, and when he loses, it will be 0. So this term will just vanish. Is this all right?
Yes.
Okay, so we'll just forget about this. Now, you see, we know this value. We know the value of utility he is getting when he is winning. What we have to obtain is the probability of winning. Now, the probability of winning is important to understand. How will we obtain this? When will he win? When will player 1 win? When will he win? He will win when B1 is greater than all Bi, where I belongs to 2, 3, 4 dot dot n, or equals to, you can say, doesn't matter. When it is more than all the other bits, then only he will win. Is this all right?
Yes.
Now we don't know the distribution of B1, but B1 is a function of V1, so we can just substitute V1 is greater than Vi cube, where I belongs to this. Is this all right?
Yes.
Now you see, we know the
Basically, because we have been given that they are bidding VIQ.
yes, we are given Vi cube. Now you see this event 2, 4 dot 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 n. What is this event? This event is B1 is greater than equals to B2, B1. So I'll not write comma, I'll just write it like this. Intersection B1 is greater than equals to V3, intersection B1 is greater than equals to V4, intersection B1 is greater than equals to V5, dot dot dot, intersection B1 is greater than equals to Vn. Is this all right? This event is all right,
Yes,
right?
fine. Yeah.
Now, when you are trying to calculate the probability of this event, because what are we interested? Probability of winning. When will he win? This is the event of winning, and we are trying to calculate the probability of this event, right? Probability of this event. Is this all right?
Yeah. That's the
So
product vector.
this is one event, this is one event, this is one event, this is one event, and so on till this event. Now you see the term is there independent. If this term was not there, you would not be able to dissociate the events and probability into probability of this times probability of that times and so on. This term is so important in this problem, you will have to understand. All right. Now what will this be? This will be probability B1 is greater than V2 times probability B1 is greater than V3 dot 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 dot, probability B1 is greater than Vn. And you can obtain this because what is this? This is uniformly distributed between 0, 1. So you can obtain each of these probabilities very easily. It is not V2, sorry. It is V2 cubed, V3 cubed, is cubed. I'm sorry about that. All right. Is this all right?
Yeah. Okay.
Now you see probability B1 is greater than equals to V2 cube times probability B1 greater than equals to V3 cube. So until probability B1 is greater than equals to Vn cube. These probabilities are very similar to these probabilities. See, not here, over here. When I say this part, B1 is greater than equals to KV2, something like that, right? We are obtaining that probability. B1 is greater than K. It is not V2 over here, V2 cube. So you have to use that concept, and what you have to do is you will have to say this probability B1 is greater than equals to V2 cube is actually probability V2 is less than equals to cube root of V1. Is this all right?
Yes.
And then you can use the probability distribution function, whatever it is, and then solve this problem, multiply this times this time this, you can obtain the probability of winning, and you can obtain the utility, expected utility, then you can obtain, you can differentiate the expected utility, and then you can, when you differentiate, then you can obtain the best response. So this is how this problem will be solved. Any questions?
Okay.
All right. So you have a problem like this in the assignment. I hope you will be able to solve that problem.
Okay.
All right. Then we'll move on to the next question. This question you can solve. So just read this question first. By the way, this terms I have written it incorrectly. It is not average value of this. Okay, it is just expectation of this. I just correct it. Expectation is actually average value. So find the expected value of v square. That is the question. So we have discussed this all along. Expected value of a random variable x is what? Could you help me? Are you here?
Yeah, I'm here.
So how will we calculate expected value of x? Okay, I'll help you. It is summation of the value x takes times the probability mass function or distribution function. You see, when we have a discrete random variable, it is mass function. When we have a continuous random variable, it is a probability density function. So you see over here it is interval. So I'll just not write p of x and not sum also. It will be integration x f x of x. I have removed summation with integration because summation is for discrete, integration is for continuous. Probability mass function. So P capital X of X. This is probability mass function. This is defined for discrete random variable. We have F capital X of X. This is defined for, this is actually probability density function. Okay, this is defined for continuous. So this is for discrete and this is for continuous. Okay. Both are kind of similar things. So this is the expectation of x. Now what we have to calculate? We have to calculate expected value of v square, right? What will this be? This will be v square f capital V square of v square. Is this all right? Or I can say x is equals to v square. Expected value of x is what? Integration x f capital X of x. Is this all right? So as a minus infinity to infinity. All the steps I have, all the equations I have written are the same things. Is this all right?
Okay.
Right. So you see over here, capital X is equals to v square. We don't know this distribution function. We don't know that, right? We are not known what is the, so we are given, we know that f, so we know f y of y, or I'll just say v. We know about capital F, capital V of small v. We know these kind of distributions because we had discussed this distribution when it is uniformly distributed between the interval 0, 1. We don't know what happens when v square becomes. So for that, you can use a law which is known as law of unconscious statistician. By the way, this problem I have not taken from anywhere. This is a problem which was given in previous year assignment. So this is not from anywhere like that. Okay. So I'm using law of unconscious statistician. What does it say? It says that if you have a random variable x, which is a function of another random variable, you don't need to obtain these kind of distributions. You can just use the distribution of previous random variables. What you have to do is, instead of v square, you just write v. Instead of v square, just write v and use the distribution of capital V of v. So you don't have to go to v square and all those things. You just use this. When you do this, so you see you're changing this also and you're changing this also. When you do that, then you can easily obtain the expected value of x. It is just change of, so when I write x is equals to a function of y and you're calculating expected value of x, what is this? Integration minus infinity to infinity small x f capital X of x. This is what? Okay, I'll just say g of x. Okay, now you don't know the distribution of x, but you know the distribution of y, the distribution of y. So you just do integration y f y of y. If you know y, you don't have to go to the distribution of x. That is what it says. Is this clear? Am I confusing you? Is this confusing? I guess I'm confusing you.
Yeah, there's too much algebra running.
Okay. Okay, so yeah, so this is not a question on game theory. If you want, we can skip this because this is not a question of game theory. This is a question
So
on
we can
probability.
complete it if it has come in the assignment exam last year.
Right. So this is a problem of last year, not this year. So if you don't understand law of unconscious statistician, it will become difficult. And I am telling you, this is not a question of game theory. This is a question on probability. So you can just skip this. Okay.
So let's complete
Instead
it.
of
So the
two,
answer is instead of x fx dx, it will be v fpdv, and that's the
no,
answer, is it?
I am saying it will be v square. It is not v square. I'm sorry, it was
But that
v square.
unconscious guy is telling us to go from v square to v. So
Uh-huh,
that's the answer.
right. So if you do this, you will get expected value of v square. I just don't want to confuse you further because the next question might be more involved.
So then v fpdv, how do we do that, or we leave it at that?
So no, we actually know. So when we are saying so you see, when we are saying we have a uniform random variable which is between 0 and 1. Suppose x is the random variable which is between 0 and 1. It is the density function is given by 1 for the interval 0, 1. And it is given by 0 otherwise. Okay. So this is how the density of that random variable, which is, so x is uniformly distributed between 0, 1. If you integrate this, you will see. So integration, so f of x is what? Integration of f of x. This is, so this is distribution. This is distribution function. This is density function. Okay, so if you integrate it from minus infinity to x, you see this will become minus infinity to 0 fx of x plus 0 to x fx of x. So this will become 0, and this is what? Integration of 1 from 0 to x, which is x. You see, we had known this. When you say the distribution of a random variable which is uniformly distributed between 0, 1, it is the length of the interval x. You see, we are getting x. Is this all right? Is this all right?
But we had x fx dx there.
There are a lot of x over here. That is why it might get confused.
No, in that earlier when it was x, it was fx.
So, for example, our valuation, when I say fv of small v, what is this? What is the value of fv of small v? Is v, right? When I say fv of 2b in the example, in the class, it becomes 2b, right? So when I say this is randomly distributed between 0, 1 and this is 2b, the probability this distribution is given by 2b, the length of the interval. The distribution becomes the length of the interval, right? You could unmute and speak. I can clear your doubt in that way.
If you go on the left hand side, that thing that you had written v square, you replace it with x, and then it was integral minus infinity to the infinity x into this v, x into fx of x.
You
So
see,
now it is minus x.
this is expectation. This is not this density or distribution. This is expectation. This function and that function are different. Over here it is expected value of x. Over there the distribution of capital X. That is why I was saying it might confuse you. So should we skip this problem?
We just complete it and finish it off. There are others also who might see on the recording.
Sorry?
So you can complete this and finish it off because there are others also who might see on the recording.
Right, right. Okay. So we will skip this problem. Now we'll go to expected revenue. Okay. Now you see we have n number of bidders and this is a first price sealed bid auction. Each PI, which is the valuation of a player, is independent and uniformly distributed between 0, 1. So you have independence, you have uniform distribution between 0, 1. What is this expectation? Summation of I equals to 1 to n v cube. So this is the question. Okay. So you see, whenever you have expected value of summation of something, you can take the summation out. You can take the summation out. For example, if you have expected value of x plus x square, you can just do expected value of x plus expected value of x square. Okay, so you can do this. So you can take the summation out of the expectation. Okay. So this will be given as, this will become summation of I equals to 1 to n expectation of v cube. Okay, this will become this. Is this clear? Is this clear?
Yeah.
Now, this sum, we will worry about that sum later. What we have to do, we have to calculate expected value of v cube. In the previous question, we were just doing that. Integration of minus infinity to infinity, we will write v cube and small f of v. This is actually 1. When it is 1, when it is uniformly distributed between 0, 1. So it is just 1 dB. This density function of a uniform random variable which is distributed between 0, 1 is 1. For that value 0, 1. And for all other value it is 0. So this is the density function. This is the density function. So I am just writing this. So I have just written it not correctly. It will not be 1 for all values. It will be 1 for 0, 1. So over here I will just say f v of v, and we will write minus infinity to 0 v cube times 0 dv plus integration 0 to 1 v cube times 1 dv plus 1 to infinity v cube times 0 dv. All right.
Yes.
So these two parts will just vanish and we are just worried about this part. What will this become? This will become v to the power 4 by 4 0 1, which is actually 1 by 4. Right? Now you see this expectation is coming out to be 1 by 4 and we are summing it from 1 to n. So it will be n times 1 by 4. Summation of I equals to 1 to n of 1 by 4. What is this? 1 by 4 plus 1 by 4 plus 1 by 4, n number of times. So it will just be n by 4. Is this all right?
Yes.
So this answer is n by 4. And if you go back, if you are trying to imagine this will just become integration of minus infinity to infinity v square f v of v dv. Now again we'll just do the same thing. It will be minus infinity to 0 v square into 0 dv plus 0 to 1 v square times 1 dv plus 1 times infinity 1 to infinity v square 0 dv. This will become 0. It will be v cube by 3, 0 and 1. So it will be 1/3. So this will be the answer. No option is there. So this is 1/3. Okay.
Yes.
All right. So this is a second prize seal bid auction. In second prize seal bid auction, the highest bidder wins, but he bids the second highest amount. So you see, this question is little bit different than what was discussed in the class or the lectures. You see, the question is so that the second prize sealed bid auction, and it is Bayesian by the way, right? So this is a Bayesian game where the valuation of the other players are not known. It is a weakly dominant strategy to bids one's valuation. That is, BI is equals to VI for all I. So this is for all I. So we have to show that this is the weakly dominant strategy. We know that BI is equals to VI for all the other players is a Nash equilibrium. We know that, right? BI is equals to VI for all the other players is a Nash equilibrium. Is that all correct? The second prize seal bid auction.
Yes, it is equal to 1. Yeah.
Right. Now we will show that it is not just a Nash equilibrium, it is a weakly dominated Nash equilibrium. So it is actually a kind of a dominated strategy. Which dominated strategy? A weakly dominated strategy. Okay. All right. So we will show that. You see, when I talk about player I, so we are talking about a specific player. So let me write capital I or something. What should I write? For a specific player, I'll say J, a player J. So when I'm writing I, it is for all other players. When I'm writing J, I'm talking about a specific player. Okay, so player J. Or we can fix player 1 also, doesn't matter. For player I, so when Bj is greater than Bi for all I not equals to J. So what does it mean? All the other players are playing, it will be Vj. So just a minute. Okay. I'm just confusing. Okay, so for a specific player J, I'll just write it like that. For player J. Okay, for player J, there can be two situations. Situation one is when his bid is more than Vj. Situation two is when his bid is less than Vj. So we can give equality in either of the side, this side or that side. It doesn't matter. That is why I'm not specifying any equality. Only two conditions can happen. Either Bj is greater than Vj or when Bj is less than Vj. Okay. Is this all right?
Yeah.
Right. So you have, suppose there are n players. So suppose there are n number of players. We are not talking about 2 players now. We are talking about there are n number of players. And the second highest bid, suppose it is h. Suppose the value of that second highest bid is h. Okay. So in first condition, there can be 3 more conditions. The first condition is h. I just refer to my notes. Otherwise, I may write h is more than Bj, which is more than Vj. Bj is more than h, which is more than Vj, and Bj is more than Vj, which is more than h. We will draw a table to understand this clearly. So this is the table. So, so in this column, I'll write the value of h. In this column, I'll write the value of bi and or bj and vj. Okay. So suppose over here we have h as 110, another condition when h is 95, another condition when h is 80. So when bj is equals to 100 and vj equals to 90. So what is the case? You see, when we are here h is 110, bj is equals to 100 and vj is 90. So we are in case 1. So we are in case 1. Okay. When bj is equals to 100 and vj is equals to 90. So what is the utility? What is the utility over here? What is the utility? You tell me. What is the player? Does the player win? First tell me that. In this condition, does the player win?
H is the second highest bid. That means someone else is going to win. No? The highest bid is someone else.
So in this case, when this, you can say the bids other than J. So just let me replace it. Bid other than highest bid other than BJ. Then we will be clear. So it is the bid other than BJ, highest bid other than BJ. So in this case, does player J win? No, right? Player J will not win because there is a bid which is higher than his bid. There is a bid H which is higher than his bid.
So he is not player. He is player I. The guy who is bidding.
BJ is the player J's valuation. BJ is his bid, and H is the highest bid except his bid.
And we are calculating for player J. Okay, fine.
Player J. We are talking about player J. So does player J win? No. Over here, does player J win when he is bidding higher than all the other bids? Does he win? Yes, he wins. Right? Because he is bidding higher. Is this clear? The highest bid.
Yeah. Okay.
Except
H
his
is
bid.
Okay. The other players. Okay.
So take this example. Suppose H is 95. He is bidding 100 and his valuation is 90. He is winning, right? He is bidding 100 and the bid except his bid is 95. The highest bid is 95, right? He is winning. He is winning, right? He is bidding 100. All the other has player, the highest bid is 95. So he's winning. What is the utility? Utility he is getting is -5 because his valuation is 90. The utility is -5. Is this correct?
Okay. Yeah.
In this case, he is winning or not? In this case, he is winning or not? Suppose the bids of the other player, the highest bid of the other player is 80. He is bidding 100 and his valuation is 90. He is winning.
Yeah.
He is winning, right? But what is his valuation? His valuation is 90. He is paying 100. No, he's not paying 100. He's paying 80.
Second highest.
Paying 80. Second highest. He's paying 80. So the utility is 10, right?
Yeah.
Okay. So his bid was, BJ was 100 in this case. Suppose his bid was 90. So he is bidding exactly his valuation. In the first case, he is bidding a value higher than his valuation. In the second case, he is bidding a value exactly equals to his own valuation. So you see, in the first case, when he is bidding 90 and the highest bid was 110, he is losing, to his utility is 0. In this case, when he is bidding 90 and the highest valuation was 95, he is getting a utility of 0 because he is losing. And in this case, when he is bidding 90 and the highest bid except his bid was 80, he is winning and he is paying 80. So his utility is 90 minus 80, which is 10. All right.
Okay.
Now you see the utility for this two conditions. See it very clearly. So when he is bidding, when he is bidding exactly his valuation, his utility is either same or more than what he is getting when he is bidding more than his valuation. Is this correct? When he is bidding exactly his valuation, the utility he is getting is more than or equal to the utility he is getting when he is bidding a higher valuation. Bidding
Yeah.
is
Okay.
right. So this bidding bi is equals to vj in this case is weakly dominating bj. So bj equals to vj is weakly dominating bj greater than vj. We have established this fact.
Okay.
Now over here also we'll have three cases. The first case is when h is more than vj, which is more than bj. The second case is bj is more than h, which is more than bj. And the third case is bj is more than bj, which is more than h. Okay, so we'll have uh, one more condition, which is 60. Then we'll all have this condition. You see, in this case, his bid when he is bidding 100 and his valuation is 90. Okay, this cannot happen, right? So we'll change this also. Suppose this is 80. So when he is bidding 80 and his current valuation is 90, so this satisfied this condition. Now we'll consider three cases: when h is 95, when h is 80, and when h is 60. Okay, these three cases we'll consider. All right. What are we trying to do? We are just trying to show that bidding his valuation is the weakly dominated strategy. We have shown this when bj is more than bj. We'll have to show the same thing when bj is less than bj. That is it we have to do. If we show that, then we are done. We'll say that bidding his own valuation is a weakly dominated strategy.
Okay.
So we'll do the same exact thing in this example also. So let us see if we have the three cases or not. So we are saying that h is equals to 95, vj equals to 90, and
So
bj
first we'll
equals
do
to.
yes, no, yes. No. Whether here he's not going to win over here.
So I was writing winning or losing because that is how we'll calculate the utility. I'm just I'm just checking if we have all the three cases or not. Over here, Vj equals to 90, H is equals to 80, and Bj equals to, we don't have that. So let us make this 70. Let's make this 70. 70. So this is satisfied. Over here, Vj equals to 90, H is Bj equals to 70, and h is equals to 60. Okay, so we have three values: 95, 90, 70, 90, 80, 70, and 90, 80, 60. So we'll worry about this value of h, this value of h, and this value of h. All right, and we have these two values of bj and vj. Is this all right?
Yeah.
Now we'll just do the same thing. Everything will be same. So in the first case, the highest bid was 95. So he's not winning. So he's not winning. No. So he's getting a valuation of 0. So when bj is equals to 70, he's getting a valuation of 0. Okay. In this case also he's get a valuation of 0 because the highest bid was 110. Over this case, when the highest bid was 80 and his bid was 70, he will not win. He will not win, right? And he will get a valuation of 0. Is this all right?
Yeah.
Now, when he is bidding 70 and the highest bid of all the other players was 60, he is winning. Yes. and his utility will be 90 minus 60, which is 30, right?
Yes.
Yes, for all the other cases also you can see his valuation is 90 and BJ is 100. So he is winning because H is 60 and he will pay 90 minus 60. This is 30. Again, when he is bidding 90, his valuation is 90. The highest bid of all the other players is 60, then he will get 30. Okay, so we have filled this table. Again, you see this strategy is at least as good as the other strategy, right? So bidding Vj equals to Vj is a weakly dominating strategy when Bj is less than Vj, right?
Yeah, okay.
Therefore, Bj equals to Vj is a weakly dominant strategy. Is this all right?
Okay.
So this is not just a simple Nash equilibrium. This is a weakly dominated Nash equilibrium, which is a stronger concept than just Nash equilibrium, all right? And stronger than this is strictly dominant Nash equilibrium. When you have strictly, this is for prisoner's dilemma, you have a strictly dominated Nash equilibrium. This is the strongest Nash equilibrium one can obtain. The second is weakly dominated Nash equilibrium, and then comes just Nash equilibrium. All right? So these are the three cases. So this is an example of all pay auction. The players, we have two players and their valuations are V1 and V2, which is distributed uniformly between 0, 1. Which one of these three are a Nash equilibrium?
C.
C. This has been discussed in the lectures. So C is the correct answer. Okay. All right. So this is all I had planned for today's discussion. I know today's discussion was a little bit confusing, I could say, because I had to go to probabilities and all. If you feel that it is not clear, you can ask me in the next lecture hour or sessions. I can clear that out about probability. Okay.
Okay. Thank you.
Thank you so much for joining. I'll just end the meeting now.